Welcome to Mathematics 058, which is Introduction to Quantitative Reasoning. Our first lesson is section 4.1, and we're looking at ratios and proportions. A ratio is a comparison of two quantities by division. If the units are the same in the numerator and the denominator, or there are no units, we can write the ratio without them. So what this means is that a ratio is often written as a fraction, and the fraction bar is used as the division. And so the numerator and the denominator are the top and the bottom parts of the fractions. And again, if the units are the same, then you can write it without them because the units will cancel each other out from the top to the bottom. A rate, however, is a ratio with different units in the numerator and the denominator. The units should always be written when working with a rate. And a proportion is a statement that two ratios are equal. And to symbolize this, they say that if A, B, C, and D are real numbers, and B or D cannot be 0 because they are in the bottom of a fraction and denominators cannot equal 0 in fractions, then A over B is the same value as C over D. So we have 4 examples. Determine if they are ratios, rates, or proportions. So our first one, we have 5 to 9. The word 2 is where our ratio or our fraction bar would go. So we have 5 to 9 that we can write this way, which would give us a ratio because there are no units written. For B, we have 25 miles over 1 hour. Notice miles and hours are different units of measurement, and so that is where we have a rate. C is comparing two rates, and it's saying 4 gallons is to $14 as 10 gallons is to $35. And so the key factor there is that equal sign, so we're comparing two of them, and that gives us our proportion. And then D, we have 18 feet over 20 feet. And for that one, we have labels, but this time they are matching. So we have feet over feet, and it told us that we don't need to write them because we can cancel them out top to bottom. So we could write this ratio as 18 over 24. And we could even simplify it if we wanted to. Usually we simplify all ratios and rates to simplest form, just like we would simplify fractions to simplest forms. And with this, 18 and 24 are both multiples of 6, and so 18 divided by 6 is 3, and 24 divided by 6 is 4. So we're really looking at a ratio of 3 to 4 when we reduce that. But again, that means it is a ratio. A proportion is considered to be true if the ratios on both sides are equal or equivalent fractions. Otherwise, the proportion is considered to be false. Suppose you have the proportion 10/15 equals 18/25, and you want to compare the two ratios to determine if the proportion is true. Two methods can be used to do this, and they're explained in problems 2 and 3. For number 2, the first method, since the ratios can be thought of as fractions, one way to compare the two ratios is to find equivalent fractions for each by using the least common denominator, or the LCD, and then compare the numerators. And so For A, what is the LCD for 10/15ths and 18/25ths? So let's look at our denominators. We have 15 and 25. So we're looking at the least common denominator. And so what we're going to do is we're going to look at the bottom numbers until we can find the first number that those two divide in evenly. And many people want to confuse that with the greatest common factor, the largest number that divides into those, and that would be 5. But we're looking at changing these and making them bigger if possible. Sometimes it might stay the same, but at least being the same or bigger, that would be a multiple of both of them. And so what you can do is start listing the multiples of one denominator. So for 15, we would list 15 as our first multiple, which is 15 times 1. Then 15 times 2 is 30. 15 times 3 is 45. 15 times 4 is 60. And 15 times 5 would be 75. And 15 times 6 is 90. Let's see if that's enough. And let's list the first several multiples of 25. So we have 25, 50, 75, 100, 125. So we're just counting by 25s, and then for the least common denominator, we're looking for the smallest number that they have in common. So if we look across our multiples, we see that 75 is the first one we have in common. So our LCD is going to be 75. Now we need to find equivalent fractions using our LCD, or using that 75 from part A. So they were giving us 10/15ths for our first fraction, and what they're telling us is we need to find a fraction that's worth the same amount when using 75 as a bottom number. So we need to find out what we need to multiply to get from 15 to 75. If you're not sure, you can do 75 divided by 15 to find that out. But it was 15 times 5 to get to 75. And so in order for them to stay equal, what you do to the bottom of the fraction, you have to do to the top. Because if we look at 5 over 5, that's the same as multiplying by a unit that's equal to 1, because we know anything divided by itself is 1. So since we're multiplying by the same number, we're just renaming the fraction, we're not changing its value. And when we do that, 10 times 5 will give us 50. And so we found that 10/15ths is worth the same amount as 50 over 75. And let's do the same thing now with our second fraction. We had 18/25ths. So again, we want to get a common denominator, which will be our 75. And then we need to find, what are we going to multiply to get from 25 to 75? Well, I think of quarters, and there's 3 quarters and 75 cents. So again, that means we have to multiply the top by 3 as well. And so 18 times 3 gives us our new numerator of 54. And so is the proportion 10/15ths equaling 18/25ths true or false? It is false because we found our equivalent fractions of 50 over 75 is not equal to 54 over 75. So equivalent fractions are not the same value, and so therefore our proportion is false. They're not worth the same amount. So another method, or another way to determine if a proportion is true or false, is to clear the denominators, or to make our numbers to where they're not fractions anymore. To do this, we need to multiply both ratios by a whole number that reduces both denominators to 1. While this number does not need to be the LCD, using the LCD will keep the numbers smaller and easier to work with. And so if we find the LCD of 10/15ths and 18/25ths again, we could go through the same process, but we would still get that same result of our LCD equaling 75. Now it did say you could use any number as long as it's a multiple of both. So notice that 75 was the smallest number that we could find when we went through our list, but actually if you used 15 times 25 and used that number instead, you would get a number that works, because obviously you multiplied the two numbers together. And so that number would be 375. Again, obviously that's a lot larger number to work with, but it would still get you the same results if you're not sure how to get the smallest results. And so if we're using that, if we multiply the ratio of 10/15ths by the answer to part A, we must multiply 18/25ths by that same number, or the resulting equation will not be equivalent. And so we're going to multiply both sides by 75. So we have our 75 times our 10/15ths, and that's supposed to give us the same number, if they're equivalent fractions, as taking that 75 and multiplying it by our 18/25ths. And when they said we can get our denominator down to 1, this is how. Any fraction can be written out of a whole number if you use a denominator of 1, because anything divided by 1 stays the same. And you can simplify fractions by dividing the same thing from a bottom number to a top number. So we know that 15 goes into 75 evenly, so we can divide a bottom number by 15, and 15 divided by 15 is 1. And we'll divide 75 by 15, and 75 divided by 15 is 5. And then notice we have only ones when we multiply the two denominators, and again anything divided by 1 stays the same. So on this side we can just do 5 times 10 to get 50 and not even worry about writing that denominator of 1. And on the right hand side, again, we know 25 goes evenly into 75, so let's divide 25 by 25 and get 1. And 75 divided by 25 is 3. And so, yet again, we have just ones in the denominator, and anything divided by 1 is the same, so we'll ignore that and do 3 times 18 to give us 54. So now we have a statement that says 50 equals 54. And so we know that this is false as well, because they're not the same. And actually, if we look at that compared to part A, our numbers from part A, or I should say the numerators from part A match the numbers we get in part B. So we had 50 over 75 equals 54 over 75 earlier. The comparison values you get from both methods may be different, but both approaches are valid to use. What do the methods have in common? They both use the LCD, the least common denominator. And then which method do you prefer? Why? Well, that's a preference that only you can answer, and describe why. However, we're going to go over a second way to be able to tell if two fractions are equal to each other, so if a proportion is true or false. And I believe that this will be your go-to method because I think it's a lot simpler than using either way that we just looked at. So our new method is looking at cross products. The cross products of two ratios in the proportion A over B equals C over D is found by multiplying A times D and B times C. And you can see an illustration that they're across from each other. That's why they're called cross products. And it doesn't matter which way you list them or order them, it's all going to be the same. So for example, what I mean by that is if you write C times B is the same as A times D, we know order does not matter in multiplication. They are commutative. It means you can flip them back and forth. 2 times 5 is 10, the same as 5 times 2 is 10. So it doesn't matter which one you list first and which one you list second, or which side you list it on, as long as you're putting the A somehow with the D and the B somehow with the C. So now we're going to look at our example that we've been looking at. Our 10/15 equals 18/25, and using the cross product. We already know that this is false because we've proved it twice. So let's see what happens when we do our cross product and what we will see to show that it is not a true statement. So let's do our 10 times 25 on one side. I'm going to use parentheses to show multiplication. And then the two that are across the other way are the 15 and the 18. So when we do this, 10 times 25 is 250, and that is the same as 15 times 18, which is 270. And no, it is not the same, which again, we already knew that because we knew that this was a false statement. So it's not equal, and so it is a false statement. And it asked, did we get the same results as we did for part B of problem 3? Well, it asked if they were the same, and we were looking at the 50 equals 54. So we're not using the same numbers, no, but we still get the same final results that no, they are not equivalent. So here's some examples for you to try. Here you're telling whether the given is a rate or a ratio. Notice it tells you to reduce down to lowest term. And then you have proportions to work with. And if you need help with number 11, then that's something that you can do in a calculator. If you need help learning how to type that in the calculator, YouTube is a wonderful place to learn how to do that. The TI-30s are probably the easiest calculators to work with using fractions. And otherwise, pause the video and work those out. The answer key is in Canvas under the Files tab if you want to take a look and check your answers. Otherwise, when you're ready, unpause it and move forward, and we'll look at some story problems together. So our first story problem says Lachlan is comparing nutrition labels to see if two products have equivalent ratios of calories per serving. The first product has 110 calories per 80 gram serving, and the second product has 82.5 calories per 60 gram serving. So we're supposed to set up a proportion and then find if they have equivalent calories per serving. And so let's set up our proportion. Here it tells us we have 80 calories per is where our fraction bar will go. 80 110 calories per 80 grams. And so let's put that here, 110 calories over 80 grams. And we're supposed to get the same amount as, let's see, 82.5 calories per 60 grams. So 82.5 calories over 60 grams. And we can find the cross product, the easiest way to do this, to see if they have the same calories per gram equivalency. So we're going to multiply our 110 by 60 to see if we get the same as 80 times 82.5. And so when we multiply, we get 6,600 on the left. And when we multiply on the right, we also get 6,600. So yes, the two products have equivalent calories per serving ratios. Another way to compare ratios is to convert them into unit rates, which is the equivalent ratio with a denominator of 1. You can convert a ratio to a unit rate by dividing the denominator into the numerator. Convert the ratios on both sides of the proportion into a unit rate. And so what we would want to do to get this is to take our 110 over 80 and divide both numbers by the denominator. So we're going to divide our 80 divided by 80 to get 1, and 110 divided by 80, and we get 1.375. So that's 1.375 calories per gram, or per 1 gram serving. And we'll see if we get the same for the other one, which we know they're equal, so we should. But let's just try it anyway. We have 82.5, and that was over 60. So it means we're going to divide by 60 over 60 to get that denominator into a 1. And 60 divided into 82.5 also gives us 1.375. And so again, that's telling us that's how many calories per gram of the nutrition. And so, do the two products have the same number of calories per gram? They sure do. Example with concrete now. When making concrete, the ratio of sand to cement should be 5 parts sand to 2 parts cement. A batch of concrete is made, that's a typo arrow, with a ratio of 30 parts of sand to 14 parts cement. Set up a proportion using the given information. And so the recipe, or the directions, say 5 parts sand to 2 parts cement. And we need to find out if that's the same as 30 parts sand. Notice I'm making sure that sand is in the numerator of both, and then cement in the denominator of both. And so let's go ahead and see if we get a true statement or not. So we're going to do 5 times 14, which gives us 70. and see if that's the same amount as 2 times 30, which is 60. So no, it didn't. So the batch was not made with the correct ratio of sand to cement. We know this because the cross product are not equal. A doctor orders an IV for a patient to run at 125 milliliters per hour. A nurse sets the IV to run at a rate of 1,000 milliliters per 8 hours. Set up a proportion using the given information. And so we need to know if 125 milliliters per 1 hour is the same rate as 1,000 milliliters per every 8 hours. Okay, there's our proportion, and we're asked, did the nurse set the IV to the correct rate? Explain how you know. We can cross multiply for this one as well, and that would definitely tell us yes or no. Or you can look at this and say, my doctor orders is in a unit rate. It's out of 1 hour. So we can turn the 1,000 milliliters at 8 hours into a unit rate by getting 1 in the denominator by dividing both of those numbers by 8. And if we do that, we get 125 milliliters per 1 hour. And they match. So, yes, the reduced ratio for the nurse's settings gives us a unit rate of 125 milliliters per hour. So they matched. Our final example, a student teacher is given a guideline that a test should have an average of 6 points per problem. The teacher makes a test that is worth 78 points and it has 13 problems. So we're going to set up a proportion and see if we have a proper test set up according to the directions. So the average is supposed to be 6 points per problem, so per one problem. And is that the same as 78 points for 13 problems? And so, does this match? So again, we already have a unit rate. On the left, we can do the same thing on the right to see if that matches, or we can use a cross product to see that. And if we do that, we can see 1 times 78, which I'll even just put 78 because anything times 1 stays the same. And is that the same as 6 times 13? And it is true, 78 is the same as 78. So again, we can answer yes, the student teacher made the test according to the guidelines. It is proven through cross product to get 78 equals 78. There are going to be some problems on your Hawks Learning that go into writing your ratios using different units that you have to make the same. And so I do want to give you one example of that before we go. So for example, they might tell you to write, let's say, let's do 5/4 to $3 as a rate. Remember, your rate has to have the same units. Here, we do not have the same units. And so we either need to compare quarters to quarters or dollars to dollars. And since 5/4 don't make a whole dollar, and I like to stick with whole numbers if I can, let's go ahead and change $3 into quarters. So we have $3, and that's the same as 4/4 for every dollar. So 4 times 3 equals 12. So $3 is the same amount or is equivalent to 12/4. And so our ratio then could be 5/4 to 12/4. So then we could write that as a fraction, if we want to show our rate as a fraction, of 5/12. So 5 to 3 is not a good way to do that because, again, that's quarters to dollars, and we want to write it as a rate, which rates have the same units. And so 5/4 to 12/4 or 5/12 would be the appropriate way to write that as a rate. But again, if you have any questions while you're doing your homework, I am just an email away. Make sure you screenshot the question that you're working on so I can look at it when I answer your questions. Until next time, good night.